Hello, so in this video we're going to be using what we learnt in the last video with kind of phase portraits and how phase portraits work. So the last video was very much just based on theory, okay, but now we're actually going to apply it to one of the models that we look at in this course, and it's going to be looking at the logistic model. So actually, what does the logistic model look like? Okay, or what is a possible, graph of the logistic model? We know what the logistic model is, so now we're going to look at what the logistic model actually looks like. All right, so if I just remind you of what the logistic model was, so it was our population n. It was a model that described how our population n changed over time, so dn by dt, okay, and that was equal to our growth rate, which was just r, okay, times n, and then we had to kind of include our carrying capacity to basically show that actually our population should die off, and we showed that this model would work. Okay, we showed this model's work. So Rn times 1 minus nk. Okay, and now to actually consider this, I'm going to actually expand this thing out. I'm going to expand this thing out to kind of look at it, because it's kind of quite difficult to see what's going on here. So I'm going to say, right, okay, this is Rn minus Rn squared over k, and I'm going to actually rewrite it round the other way. So write these two terms around the other way, so I get the highest power first. So it's going to be minus r n squared, okay, over k, right, plus rn. So effectively, hopefully you can see that if I just break this line a little bit, because this is r over k times n squared, that's the same thing, okay. So effectively what I've got here is I've got a negative quadratic. I've got a negative quadratic going on, okay, where r over k is just coefficient, and r is just another coefficient. So it's a quadratic. So my rate of change of my population with respect to time using a logistic model is a negative quadratic. Okay, it's a negative quadratic involving my population. So in other words, when I try and draw this thing out, okay, so here I've got my dn by dt, and here I've got my population n. Okay, so the rate of change of my population on this axis here, and I've got my population on this axis here. That's all this is saying. Okay, it's exactly the same thing which I was doing with the phase portrait, and I now know that this is going to be a negative quadratic. All right, a negative quadratic. Well, where are the roots of this quadratic? Where are the roots of this quadratic? In other words, where does it cross? Well, the n-axis, effectively. Well, hopefully you can see that one of them should be at 0, so n equals 0, and the other one should be at n equals k. However, you can kind of do the analysis and work that out. So effectively, set this thing equal to 0, okay, and it's just basically just solving that thing, okay, so solving that thing. So what we get when we set that equal to 0, we'll get minus r over k times n squared. I'll factor out an n, okay, I'll factor out an n, so end up with n times minus r over k n plus r, okay, equals 0. So that implies that n equals 0, which gives me that solution. And then if I factor that out, so I expand that out, so I get what do I get? R equals r over k times n. Okay, that's from that bracket in there, and then that implies that n equals, and then the r's cancel effectively, and I just get n equals k. Yep, cool. Okay, so those are my two solutions. All right, but you can do that and verify that for yourself if you wish. Okay, so basically I know that those are my two roots. So therefore I know that I've got a negative quadratic going on, and it's going to cross at n equals 0 and at n equals k. So let's see if I can draw this in. There we go. That's not that bad. Okay, so this is n equals 0 and this is n equals k. So that's all I'm just doing. It's just basically algebra, which you should have been familiar with since A-level. Okay, now let's look and see what happens. So for this side of the axis over here, okay, I'm going down like that. Okay, I'm going down like that a little bit, so just extend it. So this side of the axis over here, what's happening? Well, dn by dt is negative. Yeah, dn by dt is negative. It's going down like that. So therefore, if I just draw, draw my thing down here, so my phase space, so this is my equilibrium point here, should be k, because that's when dn by dt is equal to 0, when we're crossing the axis. Okay, so there should be an equilibrium point there, there should be an equilibrium point there at 0. Okay, now when I'm this side of the axis, so when I'm to the left, over here, okay, I'm negative. My dn by dt is negative, so my rate of change is negative. So what does that mean if my rate of change is negative? It means that my previous time step should be bigger than my last, or my next time step should be smaller than my previous time step, right? So basically what I'm saying is that I'm moving away from this equilibrium point. Okay, then let's consider in this region here, well, my dn by dt is positive. So if my dn by dt is positive, that basically means that my next value should be, or my next n value should be bigger than my previous n value. Okay, so that means that basically I'm moving to the right. Okay, so my n is getting bigger. Okay, now let's look down here. So now my dn by dt is negative. So therefore that means that my previous n value should be smaller, or should be bigger than my next n value. So in other words, I'm moving towards this k point. Okay, so this is effectively what's going on. I'll just get rid of this arrow down here. I'll make it smaller, like that. There we go. So this is effectively what's going on. So this is my phase. This is my phase space diagram, you know, in here, which is going on. So what's happening at each equilibrium point? All right. So now if I just try and sketch out something which looks like that. So in other words, I try and uncollapse this n-axis into n against t, right? What's happening? So this is n against t. Below the axis, this is my axis. Below the axis, this is my axis here. This is, you know, so below my axis, so in other words to the left, I should be moving away from it. Okay, so I should be starting down here somewhere. But then I gradually move towards, 0. Is that right? No, sorry, what am I doing? Here, I should be moving away from my equilibrium point. So there's an equilibrium point here, and there's an equilibrium point, say, at k up here. Okay, and I'll just put that line in there. There we go. So I can, that's just my rate of change is equal to k. Okay, my rate of change is equal to 0. At k. So basically, at 0, I'm moving away from the equilibrium point, so I'm doing that. Okay, and I'm moving towards k when I'm between 0 and k. So when I'm between 0 and k, in that region there, in this region here, I should be moving towards k. Okay, so moving away from 0, moving towards k. And likewise, when I'm in this region here, so in this region up here, I should be moving towards k, like that. There we go. Cool beans. So this is what my solution could be based on the four-phase portrait which I've given for the logistic equations. This is what my logistic equation will look like effectively. Okay, but notice that we don't tend to just consider this case down here. Why? Well, what is this axis describing? It's n, which remember is population. Well, we can't have negative population, can we? Can't have negative population. So therefore, down here, it doesn't exist. All right. So this is just how my equilibrium point should look. Okay. And where's my stable points? Well, I've got an unstable point at 0. And a stable point at k. So in other words, what this is basically saying, or an asymptotic stable point at k. So in other words, what this is basically saying is my population, which remember modelled by this axis here, my values get bigger. In other words, they want to move away from 0 and move towards k. Okay. And likewise, we've said up here that this case up here also doesn't count. Why? Well, because we can't have a population which is bigger than k. Yeah, we can't have a population that's bigger than its carrying capacity. So in other words, we're just literally considering in this region here. All right. So in other words, what this is basically saying is that my population, and that's kind of what we would expect, so what we end up with, if I just draw this out again, because I've got a lot of writing on here, so this is k. Okay, what should be happening over time to my population is that it should be moving away from 0 and moving towards k. Okay, and that makes absolutely perfect sense. All right, because if you think about it in terms of population, what we're basically saying is as we move forward through time, population should want to get bigger, but it should start to level off. So in other words, it should move towards some value, converge towards some value, and that value is the carrying capacity, which is kind of, if you like, the absolute limit for which a population can take.